coil of wire. Yay! Right? Like, so really not scary. So, and we talked about how an inductor works, and we said that if you have a circuit that just has like a battery and an inductor, then nothing really interesting happens as long as there's a continuous current, right? If there is a current flowing, what do you know exists here inside the inductor?
Magnetic field.
A magnetic field, right? And so that magnetic field is storing energy, and we talked about how much energy that inductor is storing. So we've talked about all of that. And but as soon as, oops, I forgot to put a switch in here. Let me put a switch in. As soon as I open that switch, then there is a change in current, which means there is a change in the magnetic field, which means there's a change in flux, which means that you're going to have an induced current the other direct, right, to undo that change. Okay? That's when the inductor becomes important. Okay? It's when there is a change in current. That's like the big thing you want to remember about inductors in general. Okay? We also said that this is how your car works. We talked about that, right? And that if you just have that switch closed and then you open it, then what happens in that little space? Right, there's a little spark. That's exciting. Okay, and that spark can be used for good or can be a less than ideal thing if you're not paying attention. We're talking about a little switch that they use in a minute to help avoid that when you don't want to. So today, our topic, we've got two topics. We're talking about LC circuits and LR circuits, and I bet even before thinking about it, you can tell me what an LC circuit is.
It's a capacitor and an inductor.
Oh, that's all it is, right? It's really not a hard deal. So an LC circuit, you could probably even draw a picture of an LC circuit without my help. Go ahead and do that. Put a switch in there also, and make the switch open for now. And once you've got your picture, then check with your neighbor and see if your neighbor's picture looks like your picture.
This is amazing. I'm on the last sheet paper. The last one.
Oh, I used a front and back. Do you have a front and a back?
Yes, I do.
All right.
Exactly.
I had to do a little bit of cramming towards the end of one of them, so I'm just warning you. All right. Did your picture look like your neighbor's picture?
I don't know. Abby, what does yours look like? You should lift your hand so I can see it.
Actually, I put the older capacitor first.
Oh my God. What are we gonna do?
That's a battery.
Yeah.
You all agree or all disagree? What?
We're all like switched around. Oh my God.
Okay. Are we okay? Look something like this. Yeah. So what's going on here? Let's say that I take this capacitor, and if it's an uncharged capacitor, and I close this, then nothing interesting is going to happen, right? So that would be kind of silly, right? Like, it would just be like, whoa, no big deal. If I have a charged capacitor, that's when exciting things happen. So let's charge up that capacitor. So we'll put some positive charge on one side and some negative charge on the other side. So probably something else has to be attached at some point to charge up your capacitor. At some point, but then afterwards, not so much. What's going to happen, let's just talk this through, when I close this switch, I have a charged capacitor, what's going to happen?
Current's going to flow.
A current's going to flow. Does that make sense? I want to just to kind of back ourselves up for a second. If I have an RC circuit, we've done these before, right? Yeah, we talked about that. With a charged capacitor on it, then the current flows, and life is good, and the capacitor goes back to being uncharged, and everything, it just kind of stays no problem, right? Does that make sense? And we can look at the time, decay, all that, blah, 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 whatever over there. That's really not exactly what happens here, though, because the current flows when I close that switch. Is the current constant?
No.
No, the current isn't constant.
It decays.
It's, well, okay, so you've got this positive charge here, right? And the positive charge doesn't want to be near to the negative, so the negative's going to move, it's going to come down, it's going to come through here. We've got a change in current, which means you've got a change in magnetic field, which means you have a change in flux, which means you're going to have an induced current here, right? Okay? And that induced current is actually opposing the current that we had before, right? Because it's trying to undo what's going on.
Yeah.
Okay? And so is that negative charge just going to live here just like it would in that RC circuit? No. Because now you've got that induced current that's going the other way. And so really what happens, the really cool thing, I think LC circuits are the coolest. An LC circuit works just like a mass on a spring. It's so neat. This picture is one similar to one in your book. I just Googled this to find one that was similar because I didn't want to scan it. So just take a look over here. So when I've got a charged capacitor, it's like we have a mass that's pulled out on the spring. Do you remember this? So this is bringing it back to all of our mechanics stuff. That's what I'm saying. Like it moves it full circle, right? So you got this charged capacitor, and we've got everything's happy. I close that switch. That's like letting the mass go. It's going to get to a spot right here where you've got a maximum current, which means you've got this B field going on, and that B field is going to cause an induced current the other way. I saw her just leave. I don't know where she went, though. It's a mystery. I don't know. I just thought I'd let you know. And as that induced current is pushing the other way, it's going, so all of those, let me move that up so you can see it a little bit better, sorry. The polarity of the capacitor switches. See what I'm saying? So it was negative on the right and positive on the left. That polarity switches because of the inductor. Now you've got potential energy that's stored in the other direction. It stops from, I don't know why this box is there. That doesn't mean anything.
That's showing you where it was.
Yeah, I think they just were playing with it like in paint and I think they just forgot to delete the box. That's what it looks like to me. That's what would have happened to me. And then it goes back the other way. So now it's going to discharge the capacitor again. Are you with me there? Does that make sense? And so really what happens is that this charge, this current, oscillates back and forth. It makes a sine wave, essentially. Okay? And this is how a radio tunes to a certain frequency to get sound, I should say harness maybe is a good way to say, a sound wave so that you can hear it on your radio when it comes through. It's exactly this. Yeah?
So then induced current overpowers the initial capacitor current at some point in time?
Yes.
It switches direction?
Yes.
Okay.
Yeah. It causes the polarity to flip. Yeah. Does that kind of make sense? So it's just a little oscillator. So let's look at it numerically a little bit, and we'll see kind of how that actually happens. So as soon as I close the switch, I've now got a loop, right? A loop of a circuit, which means that I can apply Kirchhoff's rules, Kirchhoff's loop rule in particular. And the loop rule says what? Voltage around has to be 0. So we'll say the voltage on the capacitor plus the voltage across the inductor has to be equal to 0. And then we're just, instead of writing V's, let's write down things that we know. We know that the voltage of a capacitor can be expressed pretty easily, right? In terms of the charge and the capacitance? Yeah? What's that? Yeah, I'm talking specifically about a capacitor, right? So that's going to be charge over capacitance. Okay? And last time we were together, we found an expression for voltage. Let's go up if we need to re-look at it because it's been a little while since we did this before. We put a negative in front of it because we said that voltage was going to be opposite the direction it was going times the inductance multiplied by di dt. So I'm going to say that minus L di dt equals 0. Okay? So this is fun. We've got two things we don't know. Yay. We don't know how that charge, we don't know what's going on with the charge, and we also don't know what's going on with the current. So that's kind of frustrating. But we can come up with another equation to help us out. We know that I is dq dt, right? Oops, I'm going to make that a little q, excuse me. And the q's get a little bit confusing here. This q is the q that's charge flowing. Charge flowing in the current, or as current, maybe is a better way to say that. Okay. And we also know that d big Q, I'm using that Q to talk about the charge that's stored on the capacitor, or in the capacitor, is going to be equal to negative d little q. I think we talked about that before when we were doing the RC circuits as well. Okay. So we can say, if we put those two things together, we can say that I is equal to negative d big Q dt. Okay. And now I've got an expression here that relates Q and I. Is that okay with everybody so far? Okay. So if I take the derivative of this, that's going to be this thing here. So let's do it. More colors. There we go. So I'm going to say di dt is equal to d dt of negative dq dt, big Q dt. Okay. Or, what is that? Second derivative, no big deal, right? So that's going to be the opposite, actually, of the second derivative. But we're not scared of second derivatives, because we're tough. No, you're not. Why are you scared of a second derivative? Come on.
You might have to integrate twice.
No. No, this is actually really, really pretty. This is like the coolest little thing here that's going to happen.
Just want to become like the oscillation, the fun now.
It's going to be beautiful. So take a look up here. We've got this mess here. But does it make sense that I can just move one over to the other side so we can say Q over C is equal to L di dt? Yeah? I'm just going to write that down again so I don't forget. So Q over C equals negative L di dt. Oh, not negative anymore. Sorry. Thanks for catching it. Is that okay now? Yes. Okay. Oh, but di dt is just the second derivative, so we can really say that this is just Q over C equals L times the negative. There's my negative that I had lost. Okay. d squared Q dt squared. And so really, I'm just going to write that with the dq dt by itself is equal to Q, negative Q, over L times C. And this thing right here, I'm going to put a box around, and then I'll show you why I'm going to put a box around it. Partially just because it's really cute. Oops. So cute, right? You're like, wow, that's really cute. But partially because last semester we did see something that looked like this.
Here the Q is our
Yeah.
and you got 1 over and the negative 1 over, and the 1 over LC is our omega.
Yeah. Stephanie, Jenny Ty was just looking for you. She just came to knock on your door. Or sorry, Jenny Ty just came to knock on your door.
Oh, okay.
I just thought I'd let you know.
Who was it?
Jenny Ty.
Okay, thank you.
Yeah. You saw this before, right? Have you seen this? Does this look familiar? You're like, maybe. If I looked in my bearings, it probably says it somewhere. This is acceleration, right? Yeah?
Oh.
Acceleration. What was this stuff? The spring constant deal, right? Okay. Saying that the acceleration was related to the displacement. Okay?
Oh.
Yeah? Yeah?
Big.
Yeah, it's been a while. But I think it's so cool because it's like, it's coming together. It's like there. What's up?
Yep, that's it. We're done. Okay, close your books.
What's that?
No. Never mind.
You okay?
Yeah. Yeah, no, I'm so bad.
So our omega squared.
So it's like, I just made that connection, like, oh.
Well, it's one of those things that, like, you know, okay, so let me back up for a second because, right, like, who does this? Who makes this make sense? So my guess, and I don't know what the history of this was, but this stuff is all just E&M, right? This is no big deal. This is just Kirchhoff's rule, and then we're applying things that we know about inductors and capacitors, and then we're solving things because we want to have one expression, and we find out that if we've got a second derivative, and the second derivative is a charge, okay, happens to be equal to this, and if you look at this, my guess is that they were like, whoa, look, we've seen this before, we've done that. Like, this has been well studied. We've been looking at masses on springs a lot, right? We get this. This thing is oscillating. We said that charge was oscillating, or that current was oscillating, and it looks very similar. There's a specific frequency, a natural frequency, if you will, with which that current, or with which that charge will oscillate, depending on what capacitor you use and what inductor you use. So that means that you can dictate what frequency it's tuned to, and that's actually what they say. And if you use a radio, so analog radios, like ones where you actually are turning the knob. Schoenberg promised me that he was going to find this thing in his back room, and you know how that goes if you've ever seen his back room. He'll find it someday. I'll let you know if he ever finds it before you graduate, all of you, from high school or college, or, you know, get your PhD. You come back and maybe we'll be able to find it at that point. But when you tune that, when you actually use the knob, what you're doing is changing the length of the inductor. And so by changing the length of the inductor, you're changing the frequency with which this thing will oscillate.
But doesn't it run out of charge?
Run out of charge? What do you mean? It's an oscillator, so it's a perfect oscillator as long as you've got no resistance in there.
But there is resistance.
A very minimal amount. So they have to, I mean, yes, there is a little bit of engineering that has to happen to make up for that, but there's very, very little resistance.
Are you trying to deny
because
the
you
existence
choose
of radios?
No, I'm just
They
wondering
don't
how
work.
it work.
It's not real.
Why do we go? Yeah.
So
I mean, does that kind of make sense? Like,
yeah.
So there is certainly a little bit of engineering that has to happen to ensure that no losses or minimal losses happen. But even if losses happen, it's the same deal as, you know, when we talked about a mass on a spring or a kid on a swing, the frequency doesn't change even if the charge changes.
Oh, so periodically you just have to
recharge
the capacitor.
Exactly. That's all you have to do. Because the frequency won't change. Do you guys understand what I'm saying there? If you have a kid on a swing, the period or the frequency with which that kid will oscillate, it has nothing to do with how big the kid is. It only has to do with what? The length of the string. Okay?
Is that 8th grade again?
Well, yeah, but that's not going to change. What's that?
8th grade pendulum one.
8th grade pendulum line. We did it in 9th grade also. We did it like a million times. So I hope that you know that. Okay? It's the same deal. It's the same deal here. The only thing that it's dependent on is the capacitor, the capacitance, and the inductance. Yeah?
What did the LC circuit say when they were about to go into battle?
What?
Charge.
Yeah.
That one is not terrible.
He didn't know that.
That is not. I mean, it's not
It's
good.
taking you the whole year to get A. That's not terrible.
Last day of new content, we can take it. You know.
Because it's awesome.
Okay.
Don't try to start anything
Wow.
critique.
All right.
I'm trying to start everything.
Yeah, couldn't you just say that joke for a capacitor, though?
It's just charge.
Wouldn't that make sense?
It would, but
It's more relevant to the material.
Oh, I'm sorry. You go
Duh.
to a comedy club and they're gonna know that. I could tell that guy was just learning LCs. That's hilarious.
I can totally see Nathan, like, senior year of college, like, touring small schools and, like, going to their physics departments and, like, telling terrible jokes. I'm sure that people would probably put you up. I don't know if they would pay you any money.
Like making a calendar, like as a hobby, and it'll just be like the tear-off calendars, right?
I
And
would
each
totally
day would
do
be
that.
like, yeah, Yeah.
New physics.
Yeah, new physics
Not-
shit.
yeah,
All
that's
right,
for
to
an
go
internship.
along with the AP curriculum. So like as you know, like the beginning of the year will just be
Bad
mechanics,
mechanics
right?
jokes.
Bad mechanics jokes, or good ones, you know, if you can find some.
As a physics major, he applies for an internship at a comedy club.
You know what? Actually, I have a former student who she just graduated with her master's in some sort of crazy engineering,
I'm not
and
joking.
It's not
and
funny
she is a stand-up comedian.
Nice.
Yeah.
Wait. She just did what?
She just graduated with her master's in some sort of crazy engineering, and has also
Realized that was pointless.
Yeah.
no, she does both. I'm like, and the funny thing was that she was like the quietest kid in my class. Like she never said anything in class. Like you know, I mean,
So
you
it's
could tell
quiet.
that she was thinking. Like you could tell that never said anything. But yeah, and now she's like, I just think it's hilarious. Anyway, okay.
I think she does engineering comedy though. I mean,
No, she does like just like random. I mean, probably some of it's sciencey, but some of it's just Anyway, all right. So as a reminder, getting back to this whole oscillation thing. As a reminder from last time that we dealt with this, when we were doing simple harmonic motion of a mass on a spring, we solved this situation. We solved this motion displacement equation and found that displacement as a function of t was equal to the maximum displacement x naught times the cosine of omega t. Does that look familiar to you?
Oh God.
I hope so. And if not, now you know what to review.
It does. It's just.
Where omega was equal to k over, or the square root of k over n. Okay. So if that's the case, then we can do a very, very similar thing over here for our new equation. So this one is being solved for q. So q as a function of time is equal to, I'm going to see if you guys can do it. Go ahead and give it a shot. I want to know what the function q of t is and what your omega value would be. Go ahead and see if you can figure that out.
Omega, or is it indifferent?
We still use omega because it's still the frequency. Yeah, it's still the frequency. Talk to your neighbor. Have a conversation. See if you can. So what are you saying? Q of t is equal to Q naught. So that's the maximum charge, right? That's the charge that was on the capacitor to start with, okay? Times cosine of omega t, right? Like, so it's no big deal. That's all it is. But we need to know what omega is.
Square root 1.
Yep. The square root of 1 over LC. Because the Q is the thing that we're kind of pulling out here, like our X. And so we're left with the L over the 1 over LC, which kind of sits in the same spot. Is that okay? Logan, did you have a question, honey?
No.
Okay. I just want to make sure. I thought I heard something and I just didn't want to have missed it. You can take this one step further if you want. You might want to. It's a short step. I is equal to d or negative dq dt, right?
There's like space here that I just didn't use, and I'm like really sad now.
What's that?
Nothing.
Use this. It's just like one line. Use that little space. Put a little.
No, it's a huge
bubble.
space.
It's like a huge space. I'm just gonna whatever. Screw
Oh.
it. I don't even know what I did.
I do that all the time in my notes. I have lots of that. Yes. So that's going to be the derivative of this mess, right? That's all it was, the opposite derivative. So you can take a derivative. What's that going to be?
Ah, good one.
This would be on, or no.
Negative Q max.
It's gonna be
Well, okay, hold on. Let's back up. So you got a Q naught,
Right.
and then what's the derivative of cosine omega t?
Omega. Omega.
Yeah. So and there was a negative, but there was a negative there. So that's just that negative. Those negatives are going to cancel out. So it's going to be Q naught omega times the sine
There we go. I used it.
of omega t.
Oh my god.
Like that should not be a huge
I
deal.
don't know where that gets us.
I feel like something.
Just so that if you wanted to know the current at any given moment, like I don't know, maybe on the problem, a problem.
Hold up.
What's wrong?
Oh yeah, no, we're good. I remember doing something like this. Oh my god, it's crazy.
Yeah, you did when we were doing
Yeah.
simple harmonic. Yes, you have done this before. You've taken this derivative before.
I feel like that should come to I naught.
Yeah, it is. Yes. Q naught omega is equal to the maximum current. Okay. We okay?
I'm a bit hungry, a bit tired.
Okay. Are you okay with the material? I guess is really the question I was asking. Yes.
Why is it not
Who
negative?
is that on the lab?
Would you use this on the lab? What lab?
Like, dynamic, something.
The lab.
This, the lab that we did had nothing to do with inductors,
Oh, never mind.
but
That alternated.
yes, yes. So no. The lab, are you talking about the ripcord generator lab? For that lab, there is no percent error. You just are drawing a conclusion based on your data.
So there's no equation.
No. I mean, you can find a relationship, but you do not have a theoretical relationship to compare it to.
Yeah,
Okay.
okay. That makes sense.
All right. Here's a problem for you.
Uh,
This is terribly practical. Did you have a question, AJ?
Her.
yeah.
What?
So does omega, like, the number, is omega measured in hertz then?
Millihenry.
Omega is the frequency.
You would
It's
say
the
mega.
angular frequency, right? So it's equal to 2 pi times f. The frequency, right? So technically, yes, it is measured in hertz.
So if I wanted, so if I wanted to, like, match it to some frequency.
Like 920 kilohertz, for example.
Yeah.
That's f,
That's F.
not omega.
Okay.
So the terribly,
Look at this.
Um,
Use the space.
give me 3 years and maybe we'll do a lab with this, right? But you guys won't be here, so sorry. You can come back and do it if you want.
Super.
Yeah.
Take an inductor, take a capacitor, choose a capacitor so that you can actually make a radio to pick up this frequency, right? Like that, we should be able to do this. I just haven't gotten around to, figuring it out yet. But, so I want to know what capacitor we want to put with that 1 millihenry inductor to find a frequency to resonate with a frequency of 920 kilohertz. Omega is angular frequency, right? So you need to relate that to this frequency, right? How are they related?
I don't know.
Pi.
Over 2 pi r. 2 pi r.
How far is
R?
is that 10 to the negative 12?
Pico?
Yeah.
I think it's negative 12. I'll look it up quick while you're done. I don't use pico very often, so it's not stuck in my head.
The accurate rate of pico.
What's the answer?
29.9 picofarad.
Answer the daily double. This would never be on Jeopardy.
But if it was, you would get it right, and nobody else would, right? All right. How we doing, team?
Alex, are scratch paper provided?
And a cast. Yeah, we did 4 times.
Questions? Issues?
We're the
What?
same, we just got 10 and they.
You typed in an extra 0.
Oh.
Oh.
Okay, so I just want to point this out, not because I'm making fun at all, but because this is one of those like classic things that you don't want to run into on the exam, right? So the conversation that I think I heard was Andrew said, I got 10 to the negative 11, and Nathan said, oh, you added an extra 0 when you typed it in, right? You guys with me there? That's what I heard. Is that what happened? Okay, so the moral of that story is what?
Don't use a calculator.
No, you can use a calculator, but what's the moral of the story?
Make sure you check what you type in.
Check your powers.
Write down what you're about to type in.
Yes, that's what you need to do. Make sure that you write it down. So if you were doing, like, if this was a piece of a problem from a free response question, right? So you would want to write something down like omega is equal to the square root of 1 over, blah, 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 right? Like you're going to write that out. And then I would write, before I do anything else, I would say C is equal to. And then I'd write down exactly what I was going to type in. Do you understand what I'm saying? Like, do that so that you make sure that you're communicating to the reader that you know what you're doing. Maybe you're not good at typing things into your calculator, but you are good at physics. Okay? If you had all the right numbers written down in a nice little statement there, and then you happen to miss a 0 or you happen to add a 0, you're only going to lose 1 point. Whereas if you just have this, and then you say C is equal to 2.99 times 10 to the negative 13th, they will not count, like that will be like, right? You know what I'm saying? Okay. Just, you know, friendly reminders.
All the greatest is consonant.
Yeah, I make that noise a lot when I'm grading it. So. Okay. Halfway done. We're gonna have so much time. All right. So Brian, I used one side of my page right there. I'm gonna start another side right now.
Oh, good.
I'm not saying that one,
I
so you're doing okay. Sweet.
I
All right.
That even with this master group that's right here. That's pretty good.
All right, LR circuits. Now, I'm guessing you can figure out what an LR circuit's gonna look like as well, yes?
I don't think so.
No?
It's gonna have an L and an R in it, right? Oh, okay. But
Left and a right.
it's just gonna be a wire.
Which
a
one?
big
Which
square,
one's which?
right? Yeah, yeah. But there are a couple of other pieces that have to be true in an LR circuit. An LR circuit is not going to do any crazy oscillation because you just got a resistor and an inductor, and they're both just pieces of wire, right? That's all it is. So it's just two pieces of wire and some other wire. Like, that's not super exciting. So we will need to have a battery involved somewhere so that we can have something interesting happening. So we're going to go ahead and put a battery in.
That's just rub the two together.
I can draw a pile of wires together too.
Right? Yeah. It's smart because it can read my handwriting well. Okay. So I'm going to go ahead and put those two pieces there. I'm going to draw this like it's drawn in your book so that you're aware. So I'm going to just leave that there for just a second. And then I'm going to go ahead and put my resistor.
What?
I'm changing colors, I know, right? I'm kind of crazy like
Why
that.
are those wires off?
I know, it's weird. Let me show you why. It's because they have a really funny switch that's added into this story.
Look, you're so small.
I know, it's like you looked at the book or something.
Single pole
What?
double throw.
It's definitely not that.
Logan.
It's set up like this.
Yep, that's it. A banana can be used to switch the circuit.
I hate
Okay.
one.
So it's like two pieces. And then the switch is going to go from one side and flip to the other side. Why? Oh, why? Right. Why in the world would you do that? Like, what function
Okay, wait, so what does it do?
would that serve? So at one point the switch is like this. And then when the switch moves, it's then like this.
Oh.
Why does it do that?
So you can create changes in current in both directions.
What happens, let me ask a question, if I have a battery and an inductor, and I might have a resistor in there too, who cares? And I put a switch like this. What happens when I have that switch closed and I open it? There's a change in current, and there's a something important that makes your car go.
Spark.
There's a spark. Okay? Sparks are nice when you want them. But if you're just trying to make a circuit go, you don't want to have a spark every time. So the reason we use this funny little switch is so that the contact is maintained here until this one has been transitioned over. Does that make sense? So we don't have any moment where it's not in contact with something.
Oh, okay.
Okay? So this switch has a name, what I can't remember.
So smart. Mega switch.
I thought I saw it, but maybe not. No, it actually doesn't have a name. It says the unusual switch. So you can call it the unusual switch or whatever. But the switch is there so that there is no spark. Does that make sense? Okay. So now let's talk about this LR circuit business. So I'm going to start the switch over here. When the switch is over here in the position, we'll call it position A, just so that we have something to talk about. Okay? While the switch is in position A, tell me what's going on.
There's current flowing.
There's current flowing, right? There's current flowing through the resistor and then through the inductor, which is just a wire, so like whatever, okay? And so nothing really interesting is happening. So when the switch is in position A, I'm going to say, just to kind of have this written down, okay? The inductor is just a wire. Inductor is just a wire. And the wire, nothing exciting happens. There's no change in current. So that means that the current is just the potential across the battery divided by the resistor.
Why is it I gone?
Because that's the current at the beginning, before I've moved the switch. Is that okay? Yeah. Call that R. The exciting thing happens when I flip the switch to, we'll call it, I don't know, position B, perhaps? Okay. When I move to position B, what happens?
No more. Just no.
So our initial reaction would be to say no current, right? But you don't just have a wire, you have a wire that's in a coil.
Yes. So there will be.
So there's going to be a change in current, and that change in current has a certain time length that's associated with it. Does that make sense? And because there's a change in current, you've got that stored energy, right? So you're going to have an induced current going in the opposite direction. Does that make sense? Okay. So there will be some time lag before there is zero current. It's kind of like when you had a capacitor and a resistor, right? And you were discharging, there was a certain time that took. It's the same kind of process that happens here. Okay? So when it moves to B, the current's going to continue for some amount of time, probably dependent on the resistor and the inductor. I mean, that would kind of make sense, right? Okay? And the reason for that is because, come on, sticker. I am stupid today. There we go. Because the inductor's magnetic field takes time to drop to zero, we'll say.
I like how when you put it in position A, you were like, it's a coil, but it's just a wire, so who cares? But in B, you're like, it's a wire, but it's also a coil.
But it's important, right? Would you agree?
Yeah.
I mean, you're right, but yes, like yeah, it's subtle. It's subtle because the coil only matters when there's what? Change. Yeah. So let's talk about when we moved it over. Boop. So I've moved that switch over. It's now in position B. Hey, look, there's a loop of wire. If there's a loop of wire, what do you know about the potential difference across the loop?
That's to zero.
Oh, okay, let's look at that.
That seems like it's important.
It often is, right? So I'm going to call it time equals 0 when the switch moves. Okay. We've now got a loop, so we can apply Kirchhoff's rules. There is some potential across the resistor because there was current, and there is some potential across, oops, that's supposed to be an L, that's an ugly L, let's try again. Some potential, come on there, carbonate, there we go, across the inductor, and we know that those have to add up to 0. Okay, well we know that the potential across the resistor is going to be negative IR. Remember we talked about that negative sign being in existence because we're looking over the resistor, not over the battery. Right, so if you do a full loop with just a battery and a resistor, IR and negative IR. And you've got a negative L di dt equals 0. I'm going to separate that out with the I's on one side and the not I's on the other side. because, you know, why not, right? So this is going to be something like di over I is equal to negative r over L, excuse me, dt. Double check that and make sure that I didn't lose anything or confuse you.
Zero, it's going.
You can see where this is going?
Let's use another layer.
Wait,
Okay.
but I have to figure out how you did that first.
Okay. I left the I on the left side, move the T to the so I can move this whole thing zoop, over there.
Yes. Oh, and then you divide it by.
Is that okay? Do you want me to go through it? I can't.
Isn't it L over R?
Did I write it backwards?
Yeah.
Let me make sure.
With algebra.
No, because the R and the DT should be on the same. They should be on the same level. Right. Here, let's go through it. Oops. Whoa. Oh.
Just leave it behind.
I'm sorry.
Okay, so you add L d I dt.
So if I let me leave the DIDT stuff over here. So we've got L DIDT is equal to, or negative L DIDT is equal to IR. Is that okay? I'm going to multiply by dt on both sides. I'm going to divide by L. Oops, not there.
Divide by I.
And then divide by I. Is that okay?
Yeah.
Okay. All right. Everybody happy with the purple thing on the bottom?
Yes.
Okay. I'm happy with it, but it's not as much fun as if we integrate it, right? Let's integrate both sides. Woo! All right.
Is it a line integral?
No, it's just a plain old no big deal integral.
Now I kind of like those DI and DT things.
I mean, they're cute, but they're not really helpful in terms of like what is the current at any given time, right? So we're going to integrate on the left-hand side from our maximum current to some current some other time. And on the right-hand side, the time is going to start at 0 and go to some other time.
That's the weird word.
Okay, let's integrate the left-hand side first because that looks like fun.
Excuse me.
What is it?
Natural.
Okay, no big deal, right?
Value.
So the natural log of I, evaluated from I naught to I. And the right-hand side, R and L are just constants, right? It's the resistance and the inductance, so that's no big thing. So that's just going to be negative R over L times T, evaluated from 0 to T, right? If we're going to be really good kids and write it out nicely. Then when we evaluate both sides, the natural log part, so that's just going to be the fraction. Does that make sense? Okay. So let's write it out one step at a time, just because we are good kids. So natural log of I over I naught is equal to negative R over L times T. And I don't like natural logs. I want to solve that for I. So what funky thing am I going to do now? Right? Like this is really not hard. Yes? So I is going to be equal to I naught because I'll move that I naught over. E to the negative R over L times T. Oh, no, not times. I lost something. Oh, I know what I did. I'm going to rewrite this real quick before I E this part.
Oh my god.
Just because they write it this way usually. T over L over R.
Clearly.
That's obvious, right?
Negative.
Yes, there is a negative in there. So this is going to be negative. I want blue.
And L over R has a fancy name.
It does.
Super tap.
Like super not fancy. But just L over R is equal to tau. And that is a time constant.
Torque and
Oh wait, you've seen this before, right? It's the same idea that we had with the RC circuit. So the RL circuit and the RC circuit are very similar in their form.
they both have resistors.
They both have resistors and they both have time constants. And if we graph it, because we like to graph things, Jack's like, yeah, that's what I wanted to do next.
Always accurate.
Yeah, they really like to graph things with time. put time over here and you put current over here, what's it going to look like?
Okay.
Exponential up, exponential down.
Exponential down.
Down, right? Okay, so you're going to start off at some I naught. After some time, oh, let's call it tau, shall we? Or we could look at 2 tau. Or we could look at 3 tau. If we look back in our notes, we can kind of process this through. We can look at situations where L over R is equal to things that are interesting. Well, if it's equal to 1, or if it's equal to that time, then we've got, I think it was something like 37%. Do you remember this from before?
Yeah, it goes down to 63%, was it?
Yeah, oops. And then after 2 tau, it's something like 13%.
Would that be I naught?
Or that should be I naught, yes, thank you.
Oh, sure. Oh, okay, that makes sense. Like, what is this? Like a percent? A weird one?
Nope, I'm just writing poorly. Something like that. And so your curve looks something like, oops, that's really not good. Try that again. Ooh, missed. Having a really hard time today.
That's like me every day.
Something like that. The graph is going to look very, very, very similar. Because it's the same shape, right? As the others.
That's crazy.
It is. So it's nice because boom, they fit together.
Slow down. I get it.
All right.
Yeah, that was going to
What's wrong?
I was just talking about how like almost every single equation we learned in the last class isn't on the equation sheet.
It's true. But we'll talk about that in a second. Hold on.
Okay.
Here's a little ranking for you to do. This is from your book. It's Stop to Think number 33.7. Rank in order from largest to smallest the time constants, tau A, tau B, and tau C, of the 3 circuits. Go. Take a look. Think about it yourself, and then we'll discuss. How about that? So, think first, then we'll discuss.
Tau is L over R, not R over L.
Tau is L over R. So why don't you think about it by yourself? Don't say anything out loud yet, and then I'll let you discuss. Just so that everybody has a chance to think and you're not just coasting. So which one is going to have the largest time constant? The one with the smallest R? So that's going to be C. So it would be C and then A and then B, right? So tau C is greater than tau A.
And obviously L over R, you want the biggest one to start as small.
Are we okay? One more. Does that make sense?
So for the R, is it total R then?
Yes. Yep. So the total R in the circuit. Does that make a little more sense?
Yeah.
Okay.
Because that parallel is the 1 over.
Right. Yeah. So the resistance goes down.
How do you measure inductance?
What do you mean? How do you measure it?
Like if you have a coil and you want to find its inductance.
We did that last time. I mean, like the physical.
Parameters.
Yeah, we did it. I don't remember it off the top of my head, but we can
Okay.
look. It has to do with the number of coils
Yeah.
and
So mu naught and
yeah.
times A.
Yeah. Does that make sense? Okay. All right, one more question. There you go.
What if you don't know? What if you don't know N?
Well, then you better count. I mean, like, it causes things to change, right? So, like, I don't know what you mean by you don't know N. The number of coils?
Yeah, like what if someone just hands you a coil? Like the one on
Then
your...
you count it, or you do an experiment to
To
figure it
measure how
out.
long, okay.
All right, the switch in the figure has been in position A for a long time.
Okay.
It's changed to position B at a time t equals 0 seconds. What is the current in the circuit at 5 microseconds? And then what is the time, or what time is the current decayed to 1% of its initial value? So this is really just, can you use that equation again, right?
Yeah.
Let's give it a shot.
Okay, so this is in the book?
This one is from the book. Yep, 3316. I even typed.
Something.
All right. So part A, what is the current in the circuit after 5 microseconds? What'd you guys say?
0.061 amps.
This is what I got.
0.061 amps. Do you guys agree with that?
Yeah.
Or like 61 milliamps?
Yeah.
Yeah? Does anybody want to go through
They don't
that?
care on the AP test.
Unless they specify.
Oh, like in milliamps?
Yeah, like how many, yeah. I don't generally see that, but yeah. And I would say if they asked that and you didn't do it, then you probably miss 1 point, right?
Oh, yeah.
At what time does the current decay into 1% of what it was before?
46.1 microseconds. What?
46 microseconds, he says. So 4.6 times 10 to the negative fifth seconds.
I got exactly half that.
Did you take
Did you use?
both resistors?
Yeah.
200?
I got 40.
I don't know. Do you want to go through it? Do you want to double check? Why don't you double check first? Because exactly half is kind of an interesting thing.
When calculating your initial current, did you use only one resistor?
Oh, yeah. You have to use both resistors for
No, you have to
No,
use
just one.
Yeah, I use one.
So your initial current is 100 milliamps,
Yeah.
and then
Did you use one resistor for tau with both resistors?
yeah, when you found L over R.
I'll find the spot that way. Oh, you did solve. I just make it.